Welcome to the lesson video on soft margins and the support vector classifier. In this video, we're going to talk about a classifier that's similar to the maximum margin classifier, but uses what's called soft margins. And so we'll start with a toy example. You look at the data set we have here, it has two classes, red and blue. And if we tried to separate these with some linear separation, you might try something through here or through here, but whatever you try, there's no linear separation that's going to work perfectly. And yet, either of these lines or something similar to these would provide a somewhat reasonable separation. And so the goal in the support vector classifier using soft margins is to extend our ideas of the maximum margin classifier, but allow for a little bit of errors in where the points can be, or think about it a little bit of there's a little bit of error that some of our data points are going to be allowed to cross those margins. So they're not going to be strict margins, they're going to be soft margins. So here's another example where the maximum margin classifier isn't going to be working the way we want, and it's going to give us some motivation for the soft margins that we use in the support vector classifier. So if you look on this data set on the left-hand side, the maximum margin classifier is going to work well here. So we have a red class and a blue class, and we have our separating hyperplane, or in this case, separating line or linear separation, and it works fine, and you can probably guess where the support vectors are and about how big the margin is. Now, if you look at the data set on the right-hand side, all we've done is add one data point, and now our separating hyperplane, the dark black line, is here. And this doesn't look very good. It doesn't seem to give the best separation between these two classes, at least not the most robust separation possibly. It gives perfect separation, but this new data point has forced it to lie right against the red data points and also right against this blue. So now our margin is much smaller, and it's probably not the most robust classification, where we have the maximum margin classifier on this side without that new data point shown as a dotted line. So this shows us that even when the maximum margin classifier works correctly, it may be too tightly optimized to that small number of points that lie right around the margin. And so soft margins are going to allow us to do something that philosophically or structurally is similar to the maximum margin classifier, but it relaxes that strict criteria that everything lie outside the margin, and it's going to not compute the separating hyperplane just by the 3 points or so that are right around it, but on larger points that are spread out further away from that maximum margin. Okay, so here's the support vector classifier. What are we doing? We're going to do something similar to the maximum margin classifier, except to use soft margins. And with soft margins, we base separation on more points near the separating plane, not just the closest few. And we're also, as part of this, going to allow some misclassified points if we have to. Why would we do this? Well, this allows us to do this classification even if there's no perfect linear separation. It's also more robust against individual observations. Because we're computing that separation hyperplane across a larger number of data points, individual data points are not going to cause error as much as they would with the maximum margin classifier. This also results in better classification of most of the data. Okay, so here's the optimization problem. As before, this should look very similar to the maximum margin classifier. This part's exactly the same, well, except for these epsilons, and we'll talk about what they are in a minute. But what we want to do is choose the betas and the epsilons and the capital M that are going to give us the maximum value for M, subject to the second line, which is exactly as before. This just makes our solution unique, and it makes the betas give us the unit normal vector to the separating hyperplane. And then this third line should be familiar from before. This is yi plus 1 or minus 1 times, this is the linear function evaluated at the feature variables. And then so the second part, this linear function evaluated at the feature variables, is the distance to the separating hyperplane, because the beta j's give you that normal vector, and it's a unit normal vector. And then that has to be greater than or equal to, as before we have m, and then we have this 1 minus epsilon. So epsilon is going to be the amount that the data point lies within the margin, or roughly speaking. And notice that this epsilon I, there's a different epsilon for every data point, right? The data points or the observations are indexed by I. That gives us the I that's in here. And so this specific data point is allowed to cross the margin by the amount epsilon I. All of our epsilons have to be bigger than 0. And then this last part here is going to help us optimize. The sum of the epsilons have to be less than or equal to C. So C controls the amount of error, the total amount of error that's going to be occurring in our margin, or the amount to which the data points can lie within the margins. So we have two plots on the right-hand side that help us to talk about this. So let's talk about some of the values that would be here. So in the first plot, we have epsilon 8 that's going to be bigger than 0, and epsilon 1 are going to be bigger than 0. All the rest of the epsilons are going to be equal to 0, right? According to this, they're bigger than or equal to 0. They're only bigger than 0 when those data points, specific data points, lie within the margins, and they're going to be 0 otherwise. In the second plot, you can see we have more data points where their epsilons are going to be bigger than 0. And when you sum up those epsilons, right, in this sum right here, that's going to give you the total amount that the points are lying within the margins. So the epsilon, each epsilon I is the amount that data point xi can be on the wrong side of the margin. This parameter c calls the total amount of wrong side of the margin that's allowed, or the total amount of errors or epsilons. And the points on or inside the margin are called the support vectors. So now our support vectors aren't just the points that lie exactly the margin away from the hyperplane. They're going to be ones that are on that margin or within it. Let's look at the effect of C. So here's 4 different plots with 4 different values of C. The top left plot has the largest value for C, and you'll notice has the most data points that are inside of those margins. These larger values for C are going to wind up with wide margins, and they're going to be considering many points in the estimation of that hyperplane. Over here we have smallest C, and they have the smallest margins, right? The total amount to which points can lie within those margins is the least, and so it's going to wind up with the narrowest margins, and it considers only points that are closest to the separation curve. And you can see the two intermediate values for C and the results for those. So as C gets bigger, your margins get wider. As C gets smaller, your margins will get narrower. Also worth thinking about, we can think about the bias variance trade-off here. So large C has the highest bias and the lowest variance. It is the lowest variance because individual points don't contribute very much to determining where that separating hyperplane is. So the separating hyperplane doesn't vary a lot based on individual points. It has the highest bias because of the trade-off. At the other extreme of the smallest C, we have examples with the lowest bias and the highest variance. And the highest variance, you can think of that in this example, just the contrast. If you vary some of those points that are close to the separating hyperplane, there's few of them, so that will have a bigger impact on where that separating hyperplane goes. So review of what we've talked about in this video. We've talked about the support vector classifier, similar to the maximum margin classifier, except we use soft margins. And it's based the separation on more points near the separating hyperplane, not just the closest few that lie on the margin. And it allows for some misclassified points. Why would we do this? This allows us to do some separation, even if there isn't a perfect linear separation. It's more robust against individual observations because the separating hyperplane is not computed just off the closest couple of points, but all those around the margins. It allows better classification of most of the data, right? It's more robust. And we talked about the parameter C, which is the most important parameter here. It controls the width of those margins. Thank you very much for watching.